Welcome back. We want to continue from where we left off with the eye, our own personal viewing device with a lens that focuses light onto our retina, and look at lenses that were invented by humans, first as devices for helping people focus their eyes as they got older to read, and then eventually magnify images. And the first documented evidence of a telescope is from 1608 in Holland, where people in the military were using a device to pull the enemy closer, a tube with lenses that allowed folks to see an image that was magnified from a distance. Galileo got wind of this in 1609 and made his own device using one he had seen from Holland as a model. With it, he pointed it to the skies, the night skies, and was able to see lunar highlands, so a textured moon as opposed to a smooth crystalline moon, which many thought the moon might have been up to that point. Moons of Jupiter, which weren't thought to exist. The only moon that was supposed to exist in God's perfect world in that period of history was the Earth's moon. And then the phases of Venus, which no one had ever seen before. And I should say, actually, in addition, one last thing, adding to the catalog of about 1,500 stars that could be viewed by the human eye. Here's the telescope of Galileo on the left. It has a converging lens at the end, which takes light and converges it to a focal point where a concave lens at the eyepiece then magnifies the image, and the image comes through in the right orientation because of the nature of the second lens, the concave lens. Here are his journal entries for observations of the moons of Jupiter in Galileo's hand himself, and Galileo's actual drawings of the moon. Whether it is your eye or a glass lens in a telescope, light, as we now know, can be refracted or bent and focused onto a specific point. When it is your eye, the image is resolved from the lens to the retina to the brain, and then you see it. But with a telescope, the light which forms an image can be magnified from the focal point to your eye, and suddenly the image can appear larger. And in a telescope, such as a common refracting telescope, you have what's called a converging lens, which is convex on either side, and it takes light and focuses it at a point where it is a virtual image, and you then take that and turn, and there's a virtual image which a second converging lens then magnifies to your retina, to your lens, where it's resolved on your retina. This first Galilean telescope could magnify by about 20 times. The second design, which is a design invented by Kepler just 2 or 3 years after Galileo, was a better design. He used two converging lenses, and then what limited the magnification was the length of the tube. And then, of course, always with telescopes, how big a lens you can make is critical. And Galileo's was not big at all. It had a very narrow field of view, and it was very, very poorly resolved at the edges. You couldn't get good focus at the edges, and you saw rainbows, and it was a difficult tool to use, but it opened up the world. And here's a diagram of that Galilean. Convex lens focuses image on a concave lens that magnifies it to the eye. And again, they're sharing a focal length, both of the lenses, and that allows the tube to be adjusted for a focus. Kepler then improves that with this second lens being a converging lens that then takes an image. Here's light going through. It's now the bottom of the image that you would see. The real object here is now at the top of the lens, and that's where it ends up in your eye. That's why it would be upside down. And the two lenses share a focal point, and in fact the focal points the focal lengths would overlap, which allows focus for different users. The next kind of telescope is invented later in the same 17th century by Newton, and it solves the problem of aberration of the lenses, the fact that it was difficult to make high-quality converging glass lenses. Instead of using those types of large converging lenses, mirrors come into play. And the telescope in this case uses mirrors to reflect light to a smaller magnifying lens or series of magnifying lenses. This would be the basic design: a tube, light enters the tube, hits a concave mirror, which bounces light off of a secondary mirror up to several lenses that converge, share a focal point, and allow magnification. This reduces aberrations. The biggest technological limitation here is making a high quality large mirror, and that's eventually solved in our modern age with telescopes that use multiple mirrors that focus independently, but then can be designed to work in unison to focus a wide field of potential electromagnetic information onto a secondary mirror. And again, the secondary mirror is very important. Perhaps the most important telescope in history is a reflecting telescope that was first put to use in 1991, and this is the Hubble. The Hubble is sent out into outer space. It actually first has some problems that have to be fixed with its mirror, and those are eventually addressed with the space shuttle going up and making adjustments and putting in some new parts, I believe. And that allowed light to enter the tube, hit the primary mirror, bounce to the secondary, and then into the light-sensitive computer chips that collected digital information, sent it down to Earth, where that information was turned into magnificent images. And here is that Hubble. Again, the door opens, the light enters, a mirror bounces it back to a secondary mirror, into the light-sensitive instruments, which then shoot, or send, I should say, relay the digital information back to Earth. And of course, anyone who wants to use the Hubble has to sign up for it well in advance and give a good reason why their request for observation of a particular part of the sky is warranted. And if they get permission, then they give the coordinates of where they want Hubble to point. And the Hubble has batteries and gyroscopes which allow it to be turned and locked on a position in the night sky. And thus, the astronomer can collect information based on their idea and share it with the rest of the world. Now, I would like to share some of that information by looking at a little video that has been made by NASA to explain some of and share some of the wonders of Hubble. So let's take a look at this. So I just want to get this blown up. Where are you? Here we are. Oh, sorry. So the camera that Hubble uses is called the Wide Field and Planetary Camera. This was put into the Hubble in the late 2000s update, and here are some of the images. Just before we get going, nebulas are gas and dust, often from stars that have already gone through a life cycle and exploded, it's saying a supernova explosion, and then they can become areas where new stars form. And our star is a second or third generation star that would have formed from the material of some star that had been in this part of our galaxy and gone through its life cycle and exploded, leaving behind the remnants of elements that then became our solar system. So you have to think of nebula as both destruction and birth and death. Places where stars are born, places where stars have lost their lives or ended their lives. So like with that last one, you're seeing the shock waves, it seemed to me, of probably what had been a nebular explosion or a supernova, I guess. Here, galaxies colliding. Again, nebula, and then we can get closer. Again, because Hubble is visible light. The electromagnetic energy that it is able to pick up is visible light. Some beautiful moons of Saturn. Mars, where the robot landed, the red planet. Storms up from Jupiter that have been raging for hundreds and hundreds of years. Areas where stars are born and stars die. You can see that there's a lot of variety in stars. Some white, some blue, some redder, some pink. It all depends on what the star is made of in terms of elements. This was a fascinating moment when a comet that was unexpected was discovered by two astronomers, Shoemaker and Levy, and they charted it and predicted that it would collide with Jupiter, and it did. And that was witnessed by Hubble. Here's the effect of that collision. Now, you have to remember how big Jupiter is in comparison to the Earth. That collision is huge. If that comet had struck the Earth, we probably wouldn't be having this conversation. We're not really having a conversation. So beautiful images from our amazing universe. Then Hubble is ending its life as a tool. Well, not really, but it's reached the limits of what it can see in the visible range, and so it's going to be replaced for exploring the deep universe with a new telescope called the James Webb telescope. Now let's take a quick look at it. So we're going to take a look at the James Webb, starting with comparing the Hubble with its replacement.
The Hubble Space Telescope and the James Webb Space Telescope will complement each other in the study of celestial objects. They are different sizes, will be at different locations.
This part is actually very interesting because we visited this location in our solar system when we looked at the Discover satellite, and this was that gravity neutral point. So the Webb telescope will be 1 million miles away, as opposed to Hubble, which has been 340. And the Webb will have a shield that blocks any sunlight from hitting the actual telescope, keeping that telescope very cool, or cold, I should say, and maintaining a temperature integrity, which is imperative or essential for the mirror. You don't want the mirror to get hot and then cold and then hot and then cold, because you get expansion and contraction.
And have different instruments that cover different wavelengths.
All right, this is also right in our sweet spot right now. As we are learning about electromagnetic radiation, we see that these telescopes use different types. And Hubble is, if we look here carefully, sensitive in a small range of ultraviolet, all of the visible, and a small range of infrared. But what astronomers wanted was to have a telescope that could see in a large portion of the infrared spectrum, and that's what Webb has been designed to do. It will view the heavens, the cosmos, the universe, in a wide range of infrared sensitivity. or wavelengths.
But together, they will help answer some of the most fundamental and inspirational questions that we have about our universe.
And with that, let's stop and look now at another video, which really then gives you some nice detailing on Webb. I think this is worth watching. It's worth you being aware of this telescope, which we hope will be launched this year.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope.
Here are the mirrors. So the mirrors, because it's so big, you can't just send one mirror up. That would break. It's very hard to make a mirror this big. So they make these hexagonal mirrors that then can be adjusted to work precisely together to focus an image on a secondary mirror.
With the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto.
This is why it needs a sun shield so that those cameras can operate effectively.
Getting this cold is done with the help of the largest sun shield ever flown. A 5-layer, tennis court-sized sun shield that blocks heat from the sun, earth, and moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang.
So this gets back to the very beginning of the year when we talked about remote sensing. And in this case, what we will be able to get as a product is a product created from infrared radiation, but then it will be we'll see false color images. And we see this often in astronomical imagery in our era, where instead of actually seeing visible light, you're seeing a false color image of ultraviolet or radio or cosmic microwave background radiation or infrared, just to name a few.
Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing.
So one of the reasons that you would have cooperation between countries on a mission like this is because with the European Space Agency giving over a rocket to get it into space, that will give their European astronomers an opportunity to actually book time with the telescope. And this is, as I mentioned with Hubble, very important. Astronomers need to be able to have access to the device, but it's very competitive, and a lot of people want time with it. So this was a way in which you're able to get more people involved and more people get access.
After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
So with that, I think we will end this segment and let you meditate on those amazing tools which exist in our world, helping us to understand our place in it.